the schedule that way. It'll be this class and next class. You have to attend all but 2 to get credit. Okay, good afternoon from the Computer Security Seminar here with CERIAS at Purdue University. Our speaker today is a recent graduate from Purdue, a former student in this class, although I understand today that he never actually got credit for being here, but he attended this seminar many times. And now that he's out in the work world, you see he's got a little shock of gray hair here, so that's what happens to you after you graduate. But graduated a couple years ago, PhD with Professor Elisa Bertino. His work was in securing data in the cloud. His talk today is titled, A New Class of Buffer Overflow Attacks. And did I mention that he was with IBM Watson? I think I did. Maybe I didn't. But anyway, Ashish Kundu.
Thanks, Randy, for the introduction. And it's always quite exciting to come back to the alma mater and give a talk and meet the fellow grad students and some new grad students. So, the last time I gave a talk, that time I was almost a graduating PhD student here who are talking about data security in the cloud. And today I'll be talking about buffer overflow attacks and system security. There's little relation with that. It's just that security does not stay with only one aspect of it. It depends on the threat model, the attack models, what you want to protect, and what are the risks. So after this was a joint work with Professor Bertino towards the end of my PhD, related to a discovery when I was working on a storage kernel, developing certain modules there. Found that storage kernels use placement new frequently. I'll describe what placement new is, and that may be exploited for buffer overflow and some other attacks. It was quite interesting for me in the beginning that this might be studied already in the literature. Fortunately or unfortunately, this has not been studied before this work, and how it can be exploited. So after that I went to, I am at Watson working on cloud security and system security in different aspects. So let me go into the details of this work, and if you have any questions, please feel free to interrupt me anytime during the talk. And I expect it to be an interactive session. Okay, you can think I'm a fellow grad student which has not graduated yet. Okay, so think that way. Okay, so I guess all of you would be knowing what is a buffer overflow, right? Can anyone tell me what is a buffer overflow? Okay, so it takes some time to warm up, I guess. Okay, so a buffer overflow is when you have a buffer, okay, and certain input or some way that buffer has been overflown, and the buffer is a memory segment. Now, why is it a vulnerability? Because when an attacker supplies an input that can be used to overflow the buffer, okay, the question is, what can you do with the buffer overflow? Okay.
Resources or overuse of resources.
Right, great. Thanks. I didn't get your name.
Tammy.
Tammy. Okay, thanks, Tammy. So Tammy mentioned that we can carry out denial of service attacks and also carry out other attacks. So in a buffer overflow attack, essentially you can pass on, an attacker can pass on tainted data that might contain code okay, malicious code to carry out such attacks. For example, Maurice Worm in the 80s was such type of an attack. And so in this example, we have an attacker sending an input data. There's an allocated buffer, and it overrides the data section from address A1000 to A1F7. Okay, so that's as simple as that. Now, if we look at in what cases the overflow can be carried out or is effective, is when you carry out stack overflow, which is quite interesting because of the way when you invoke a procedure or a function, the functional variables, the local variables, they actually are part of the stack frame, right? And before that, you push the stack pointer where you are going to return, or the return address. Okay, so that return address, if you can overwrite as an attacker, you have gotten control of execution. Okay, essentially, you have found a way to change the control flow of the original program to what you would like. Okay, so this is what you can do, is that you can execute malicious code. You can spread malware, gain control of the system. You can carry out denial of service attack, and you can access sensitive information as well. Okay, these are some of them. And then so how do you, in traditional sense, how do you overflow a buffer? Is thanks to our now deprecated libraries of C, that you can carry out string copy, mem copy. You can there are related integer overflow, then integer underflow, that can all be used to carry out some form of overflow. Okay. Now, as we show in our discussed in our earlier charts, that before the attack, okay, I cannot show you from here. Before the attack, we had the allocated buffer, and after the attack, we have the password overwritten as the attacker supplied password. So suppose you have a password checking program, okay, that reads the password and store it in the memory, which it will check, which is the original password. Okay, and it is going to check user input passwords against that memory stored information, right, which is stored from the password field here. The attacker supplied information will overflow and override their password information. So therefore, the attacker can actually fool the system or gain access into whatever system it was that was protected by the password-based credentials. So it can also supply malicious code. Okay, where first it will supply the return address as something on the stack, and the input data will contain the malicious code. Okay, so and that way it will execute certain code also. Now there are certain other type of attacks like return to glibc attacks. Okay, glibc is a common library used and packaged with many software. Okay, and by using that one, an attacker can gain access to privilege mode. Okay, so the question is, there has been so much of work, decades of work. Okay, and why am I here? What is it that I am going to tell you that you might find interesting and new? Now, there has been, for example, Professor Spafford studied the Maurice worm in 1988. It has been how many years? 24 years, going to be 25 years. Okay, it is interesting that there are other venues to exploit in programming languages and carry out buffer overflow attack, and has not been studied yet. Now, we want to provide a new mechanism that can be used all along without building on other buffer overflow mechanisms to carry out the attack. I'll focus on the vulnerability primarily and show how it can be exploited without going into the details on how to address the vulnerability. I'll just go on breadth on some of those techniques, because some of those techniques are currently being patented by IBM, so I cannot really disclose that. Okay. Okay. So let me go into the notion of object overflow. The language here we are talking about is C++. Okay. Objects, what we are going to show is that objects can be overflown, and that can be used to exploit. Now that the exact mechanism can be used to carry out stack overflow, heap overflow, as well as override stack guard also. So stack guard is a mechanism used and even implemented in GCC to detect stack smashing during runtime. Okay, that someone is carrying out buffer overflow during runtime in C, and stack guard, what it does is that it places random data, okay, before and after, or before the return address, for example, on a stack. Okay, so if you are overwriting the return address, you have to overwrite that random information, and anytime and that information is going to be used or checked by the runtime to see whether return pointer has been overwritten in an unauthorized manner or not, or a malicious manner. So in this case, we have I've carried out certain demonstrative experiments showing that we can selectively decide which byte to overwrite because of the structure of the object. It's like it's a struct, you can say, and therefore we will not overwrite the stack guard, because we know that it is always before the return pointer. Okay, so we will overwrite only the return address. So it can also be used to information leakage. Okay, information leakage, another form where you have passwords read into the memory, for example, or sensitive data, SSNs read into memory, then that memory is not cleaned, right? So one can read that memory when it is allocated to some other object. Okay, it can be used to carry out denial of service attacks through memory leakage and misalignment, which is not part of the system.
For information leakage, like how it is related to reading that memory.
Okay, so so the question was, how do we carry out this buffer overflow for memory information leakage? I'll come to that later in the charts. Okay, so these are the different types of exploits. In fact, what I would like to say is that we can carry out the whole gamut of attacks that standard traditional buffer overflow attacks can carry out, or buffer vulnerabilities can be exploited for in this mechanism. Okay, so what is the new mechanism? It's very simple. So in C++, you have two ways, or at least two ways to construct an object. Okay, how do you construct an object in C++? Can someone tell me that? How do you instantiate an object in C++?
You can put it on the stack. Well,
No, just tell me the.
what is the normal one?
Okay, okay, right. So, Michael, right? Sorry? Andy, okay. So yeah, thanks, Andy. So it is a normal new operator. It takes the class name or the number of array elements and then creates a corresponding object. Okay. The other operator is called placement new, which creates the object or the array and places at a specific address in the memory that is supplied by the programmer. Okay. Now, what it does is that I'm going to use the board here. I don't know whether you can see that. Can they?
Yeah, he'll switch the camera here.
Okay, so for example, the new operator, the normal new. Uh, Oh, you can see it there? Okay, okay, great, great, thanks. So the new normal operator is like you have a class A, you create an object A of a new A, right? It will, what it will look at is that it will look at the heap. It will allocate some memory at a heap area and then put A there, okay? So now the other one I'm talking about is placement new. Is A equals to new certain address, some address. Let's say I. Let's say I is this address. Okay. It will create the object A right here. This becomes A. Okay. So it will place by the name itself. It will place the object at the address supplied by the programmer. Okay, that address may be a constant value or can be computed during runtime. Okay, it's a non-null address. So, and the runtime or the compile time, they do not check whether the size of the object being created is limited by the size of the free memory available or not. There is no bounds checking at all, which is the fundamental reason buffer overflows occur at the first place, right? So this is quite interesting that C++ provides this kind of a construct without any security concern, and I find it kind of an irresponsible way of design a language. I mean, Strostrup is a great computer science scientist and a language designer, but at the same time, certain functional requirements need to be defined with security and non-functional capabilities in mind. And it is there are many uses of placement new, as we will see later. Okay, so this is how placement new works. That the placement new, the first one is this, and the second one is the address you pass on there.
Can you use your mouse to point to things?
Sure.
So that those who see the recording can tell what you're pointing at.
Okay. Thanks, Stanley. I'll do that. So, so if you look at what are the different uses of placement new, why is it there in the first place? Right. It is there in the first place because of let's look at your certain. You're writing a software, and you want to make sure that if software does not fail during real time due to memory allocation errors. Many times, you might have seen that certain programs cannot allocate memory anymore, right? So therefore they exit immediately, saying that there is not enough memory. So what many real-time software, reliable software development techniques propose is that allocate enough memory that is required in the beginning. Then you do your memory management by yourself. Okay. So what many software developers they do is that they will allocate memory and then use placement new to place objects in the allocated memory area. Okay. So that's for better memory management. Then for safety critical applications also. Now, if we also look at that, for better memory management, there is a concern of memory leakage, right? Memory leakage is a great concern in software engineering. So therefore, programmers often define their own memory allocation or deallocation mechanism, garbage collection mechanisms, so that there are no memory leakages. Okay, so true for mobile phones, for example. Okay, so therefore, placement new is used. The efficiency, memory allocation, anytime, whenever you call new, or malloc, it triggers you know, some amount of privileged processing to allocate memory, okay, or it will take certain performance hits. So because it might lead to page faults if you look at an operating system level, okay. So therefore efficiency is a concern there. And hardware level programming. In hardware, suppose you have a mobile phone and you are going to write a software that is that has an object. For example, let's say you are writing a device driver. Okay, you need to store an object or data at a certain memory address, because the device driver is going to read that, or the device is going to read the data from that address onwards. So therefore you need to supply that address in the code, right? So it is used in that sense. So there are a lot of important requirements for having placement new, okay. But it's a classic example where we all focus on functional requirements and we forget about security requirements, and which is why we have security is a big problem today. So any questions till now? Okay, so so the new versus placement new is the one that in the new one, it when you create an amp object, it creates somewhere in the heap. Okay, you don't know where it is. It's up to the memory management algorithm implemented by the runtime, and in the new placement new, if the variable, the address that is supplied points here, the amp object would be created at this place here. Okay, this is on stack, there's a frame pointer, and then this is on heap. So now, since we have looked at the functional issues or functional requirements that have led to placement new, what are the security issues? One is an address can be used to place a new object, and there is no bounds checking at all. That bounds, that is why overflow can be carried out, and there is no type checking. Why type checking is important? Because suppose I have in my earlier example here, I had ampersand I, I'll say int I in the beginning, right? And I am using the address of I, an integer, to store an object of class A, right? There's a type mismatch there, right? So I'm actually, so the integer I may take 32 bits or 64 bits depending on the architecture. The class A may take anywhere from 32 bits to maybe 256 bits, for example, or more than 1 kilobyte. Right? So therefore, since there is no type checking, that the size cannot be guaranteed. Actually, there is a misalignment problem. So who knows about alignment issues in software? Who can tell me what is alignment issue? So, okay, alignment is about in memory, where does your specific type start at? Okay, what are the boundaries? Okay, in C, for example, in a 32-bit architecture, the integers always start at a 32-bit at the boundary of 32-bit, like 4 bytes. Okay, you cannot have an integer starting at the boundary of 3 bytes. No, it either at 0th byte, or then goes to the 4th byte, then goes to the 8th byte, something of that. It is never 1 byte or 3 bytes. And it is a convention many times used in conjunction with the hardware architecture and the programming language or the compiler. Okay. Now that convention has to be preserved. If you want to read, let's say you want to read integer I, it will go and read from that boundary. Okay, so memory is allocated appropriately. So if my integer I, okay, starts at the boundary of 32 bits, okay, and I supply an object that that has integer in between, but those integers are actually placed at the boundary of 24 bits. Okay, I am a malicious attacker. I want to create misalignment. That means the integers are stored at the addresses or the boundaries which are not conventionally used or which are not expected by the program. So the program will crash most of the times. Otherwise, or the behavior would be undefined. Okay, so that is a way to carry out a DOS attack. So we can carry out this in this scenario. Now the other point I should mention is that memory deallocation is not trivial. Okay, because with placement new is supported by the language, but placement delete is not supported. The programmer has to write its own placement delete. And as I said, alignment issues. So how can we carry out this buffer overflow? Construction of objects we can carry out directly or indirectly, and remote serialized object. For example, I have a server implemented using C++. I have a client that sends a serialized C++ object. Okay, and the server receives the C++ that serialized object and uses copy constructor, okay, to create an instance of that object. So if the receiver program have 32 bytes, okay, it is allocated but the programmer is the attacker is supplying a 64 byte object in a serialized manner, and the server program is using placement new, it will not do any bounds checking. It will overwrite 32 bytes and then next 32 bytes it will overflow to the next 32 bytes. Okay, that is through sending serialized objects. Serialized objects are used a lot in C++ web services and many other scenarios. So then array overflows. So I have space for allocating let's say 10 characters. Okay, but the attacker is supplying 10 integers. Okay, so that will be so let's, and there are two types of overflows. One is external overflow. The external overflow is where the object grows into the space external to the memory area. Okay, the other one is internal overflow. Okay, where inside the overflow occurs inside the object. Okay, in this case I'll note that one has created an new employee object, okay, which is employee ID and account, both of them are integers. Okay, now I use the address of emp.eid to create an array of 2 integers. Okay, because I think that this object is not being used anymore. I am a programmer, I don't have much knowledge about buffer overflow, etc. I will create this two element array, integer array. It will overwrite this info2 will overwrite into the account area, because this is a single object. So there is an internal overflow happening within the object. Okay, there are other examples of it also in the paper. So there are 3 ways one can carry out overflow. One is constructing a larger object, as I gave an example. Constructing an object from a user supplied object. Okay, you take multiple objects of the users and construct an object out of them. Or construct an object from user supplied values. Okay, I have a demo actually to show how this overflow can be carried out, but I don't think I would have enough time to do that. Okay, so how do you construct a larger object to replace another object? Okay, that's the let's go into. So now let's go deep into that problem. One way to do that is use programming language semantics is subtyping. Okay, what is a subclass? A subclass of a class contains extra fields, suppose, or methods or something of that sort. So most of the times the subclass has a larger size than its superclass, right? Now we are going to use this very simple information to construct a larger object, okay? And the program allows that to do that. So let's look at two classes. One is an employee class, another is a regular employee class. The employee class contains two fields, EID, employee ID, and a character account, character array of 16 elements, okay? And the another class, regular employee, which is inherited from employee class, and it is an extra field called bonus ID. It is an array of 16 characters, okay? That's it. So that means the regular employee has all the other two members that employee has, okay? So regular employees are eligible for bonuses and normal employees are not. So that's the idea. Now suppose there is an employee management, payroll management program, okay, running in Purdue, okay, and I wish it was, and I was a grad student that I could exploit and make my salary larger. But I show how you can do that. So this is the memory space. The employee object takes this much of space, and the our employee takes this much of space. Okay. Now let's see how we can increase the. This is how we create using normal new. You created an instance of emp in the program. The program created an instance of emp. Then somewhere later in the program, okay, I am going to create an instance of the regular employee. Okay. But you know what? I say I'm going to reuse the space that I have used for the employee object already. Right? That's natural to do. Okay. I don't want to reuse, allocate more memory. So I am going to pass on the address of emp object and create the regular employee object there. What will happen? There is a data object here, which may be your SSN or maybe some password or something. The bonus ID that was there, if we go back to the previous, there's a bonus ID here. That overrides this part. Right? So we have created, the program compiles really nicely and runs. So, because of the subclassing semantics and the placement new semantics, right? So there is an overflow here, and one can carry out this attack. Now, this is a vulnerability in that program. How can you exploit it? You can exploit it only when an attacker can influence the regular employee object in some manner, okay? And so a taint analysis in such a program can determine, okay, where these, how one can influence them. So one way to do that is to construct the object, the regular employee object, from the user supplied object. How can you do that? That there's a function that asks that give me a regular employee object, okay? That can be sent as a serialized object, or can be retrieved from a database already stored. Right? Databases are used for payroll information. Right? So one can retrieve the data and pass on, invoke this method to pass on this information. One can do that easily. So there's no problem about that. Now, till now, before I go into the next level of details, I'm actually skipping a number of details that are in the paper. But till now, what have we discussed? We have discussed what is placement new, what are the security concerns, how that can be exploited. One of the specific example is how we can create a larger object in place of another, perhaps using copy constructor. What is a copy constructor? Who can tell me what is a copy constructor? Okay. Anyone?
When you want to make a new instance that has the same values, it'll hook up or allocate new memory and copy the values.
That's great. Yeah. Thanks, Andy. So yeah. So a copy constructor is the one that creates a copy of the object as a new object. So by passing an attacker supplied object, that object will be will be copied into a larger object. Now, using this mechanism, in fact, this is used heavily in kernel codes and other it's a way to it's a traditional programming practice for efficient programming. Okay, so now I mentioned, other than buffer overflow, I mentioned about how to carry out stack overflow and how to carry out heap overflow. I'll not go into the details because once you look at how buffer overflow is being carried out, where it is carried out is not that that hard to determine, right? If it is on a stack, if that object is being created within a function call, right, within a function, then it is within a stack. And if the overflow is happening within the heap, it is a heap overflow. Now, there is something else. So we can modify pointers to the variables. So let me take another example here. The example is, let's say, int a, and let's say I have star p. Okay, so main, suppose I will have a equal to 100, blah blah, p equals to new, let's say, we basically create a 16-bit, okay, 16-bit array, 16-byte array. Okay, then after that somewhere you do a obj equals to new a. So what I am doing here is that this is a variable pointer, right? I am overwriting the variable pointer by one of those one of the values. Suppose a class is like this, int k, then I have, let's say, int p, not p, p2. So p2 overwrites p here. Okay, that's a pointer. We are overwriting the address of the pointer. Okay, similarly, and overwriting the address is quite interesting because that way you can actually make the system crash directly then and there if you supply an invalid address, right? Now, a function pointer. Similarly, you can change the address stored for a function pointer. What can you achieve through that? You can actually let the program call another function instead of the original function, right? So the address, so you have actually created several functions, and there are addresses of each of those functions through function pointer mechanism in C++, right? You invoke each of those functions through those function pointers. Now if you override the function pointer, right, then you are actually, you can pass on the address of another function that you have supplied through, let's say, supplied through some other means. Okay, then you can invoke that. Right. So now there is another very interesting part is virtual pointer. What is a virtual pointer? Anyone? What is a virtual pointer in C++ object model or classes? So virtual, there are virtual functions in C++, right, which are implemented later, right? They are not defined or implemented then and there in that class. It is implemented perhaps by a subclass. Okay, so when you have a virtual class, okay, you need to pass on where those implementations of those functions are sometimes, or so that there is a need for something called a virtual pointer, and that virtual pointer after compilation GCC adds as the beginning value in the object map. So you write a program that has a virtual class or a class with a virtual function. When you compile it, the object map for those classes will contain a virtual pointer underscore vptr that contains the address where those implementations lie, for example. Okay, and that is the first set of bytes or first 32 bytes of an object. If I have an object at the before that and I can overflow that object onto this one even by 1 byte, okay, or even by 4 bytes, whatever the address is, then I am good. I can either crash the program or I can make the program execute code somewhere else, which is not there in C based buffer overflow systems, right? Either you are all scared with this, or you don't find it interesting, or the speaker is totally boring. Okay, so that is till that point was about how to carry out buffer overflow and what it can do. Okay, now I'll go into memory leakage. So in memory leakage, what is a memory leakage? Perhaps this can be answered. See, you have to ask me questions unless I will continue asking questions. Okay, I've been in the habit of taking interviews now. So what is memory leakage? Memory leakage is
You allocate memory and no longer have a pointer to that memory. So
you lose the memory essentially. So you will continuously use only 8 bytes of memory, but your program is so leaky that at the end of it, even if you have 1 gigabyte of memory, if the program runs for a long time and there is no garbage collection, you lose all the memory and the program will run out of memory. Okay, that's memory leakage. That happens when you do not manage your memory in the program properly, either in some manner. Okay, so what that means is what Andy said is that you have a look at memory and you do not deallocate them properly. That means you have lost the pointer to it. I mean, you might have a pointer, but you do not deallocate it. Now let's look at this example that I have allocated, let's say 1 kilobyte of memory in the beginning. Then through placement new, I'm going to point it to using pointer A. Okay, placement new, which takes 1k. Then after some time, it will point to with B, it will take only 512 bytes. Okay. Now, if I do not deallocate this portion, or keep track of that. I'm only, my pointer currently points to the first 512 bytes, remaining 512 bytes are still there, I can reuse it. If I do not manage it properly, I'm going to lose it, right? This is underflow. This is by carrying out underflow, and you can use placement new to carry out object underflow. That means that in the beginning you allocate 1 kilobytes and use placement new to point it to by by an object that is of 512 bytes, and lose the first pointer. Okay. That way you have lost track of this part of the memory. You have lost 512 bytes. And if you continuously do this allocation, you are continuously going to leak memory. And any program that has this kind of implementation, one can easily, and that will run into problems. So, and this happens because placement delete or deallocation of memory is not provided by default. Like in C, you have malloc and free. So yeah, calloc is used and free. So in C++ you have new and delete. You have placement new, but you do not have placement delete, because the way it is up to you how you manage the memory. Okay, so that's a lot of independence, lot of power, but power comes with responsibility. So therefore you need to manage your memory, but at the same time you need to, so therefore you have to supply, the programmer has to supply placement delete. Okay, if the programmer doesn't write a good placement delete function, then that program will have memory issues. Okay, so for example, in this case, this many bytes were allocated. Then you created an emp object here. You lost this type of memory unless you manage them. Okay, information leakage. Okay, sorry, there is a typo there. Information leakage. Okay. Information leakage happens. Suppose you have already an array that contains social security numbers of all the employees, and you create an emp in that area saying that I'm not going to reuse that array anymore, so I'm going to reuse the memory. So this part of the memory, these are the social security numbers that can be leaked. Okay, and what is the easiest way to read them? Most of the times, an array ends with a null byte. Okay, in C, unless you have a null byte, it will continue reading through it. Okay, there is no end to the string essentially. Now, if there is no null byte here, and you say that, okay, I'm going to read this as a character set. Okay, I'm going to serialize it. You have a serialized program, takes an address and serialize it. It will serialize till this endpoint. That way it will actually not only serialize the object, it will serialize the SSNs in it also. So that's the information leakage. Now we have talked about the vulnerabilities and all those things. How do you address them? One is bounce checking. If you do bounce checking, it will be easy to address it. But bounce checking is non-trivial here. Why? Because of type issues. As I saw earlier, right? I saw that there is an integer address, an address of an integer variable that you are passing to create an object there of different type. Right? So the size of the type depends on the type itself. Right? You cannot really say, okay, not these many integer array values. Okay, so you need to identify what is the type of whose instance you are creating, and inferring the type during runtime is hard, especially in C++ is not a strongly typed language. Okay, so type inference is a problem there. Now you have to carry out slicing, for example, to determine exactly what, perhaps an imprecise slicing to determine, okay, what is the largest size of this object can be, depending on what are the possible types it could be. Okay, or sorry, alias analysis, I should say. Okay, so that's one way. Mm, then for unmodifiable or legacy software, you create a new library altogether. So then propose staggered kind of solutions, and also do binary instrumentation. So anytime you have a placement, you do something else. Okay. So this is what I have. In this case, let me talk about binary instrumentation a little bit more. Why binary instrumentation is interesting? Because you have a program, let's say, and you don't have source code for that, right? So you want to address the vulnerabilities in that program, server program. Suppose you have a server that is running and you don't have source code for that, and has placement new. How would you think you can carry out handling the vulnerability? Any thoughts? So you know the binary, let's say it is stored in ELF format. Okay, ELF, and you can go and look at the binary representation of the whole program, and find out where those placement new constructs have been translated to, like what kind of machine instructions they are. Okay, and one way to do that is detect it, put bounce checking there. Now, how do you do bounce checking? Requires binary program analysis, okay, or dynamic profiling. So you use dynamic profiling to determine, okay, 99% of the time the object that is created is of the size there. So therefore you put a bounce checking with respect to that size. Okay. So that is one way to do binary instrumentation. Staggered like solutions, where what do I mean by staggered is that you have stack here and you have frame pointer. Now you have an object that is going to override. This is an object that is going to overwrite through this space and also through this space, right? Now, how does staggered work? Staggered works by putting a new byte or 32-bit data, maybe a different 64-bit data here, a random byte that it will be overwritten by buffer overflow when someone overwrites from top, right? Overwriting in a stack will always happen from the top, right? So therefore you have to overwrite here. In our case, you can selectively overwrite these variables. If you know how the program, the source code, the class structure, right? You can say, okay, I'm going to overwrite this value, I'm going to overwrite this value, I'm not going to overwrite this part, I'll leave it. So I have actually carried out experiments showing that staggered can be fooled. But we can use staggered like solutions here. Okay. Whenever you are using placement new on the stack, you can similarly supply some values, okay, somewhere before the frame pointer, and that value can be a random value or can be a hash of all the variables that are there. So you can detect if there has been violations already earlier. Okay. What that means is a hash chain. You create a hash of this value, where you can create a hash of this value, and put it here in the staggered. So even if the overflow doesn't come here, even if there is an overflow here, one can detect, oh, there has been overflow there. Okay, that is one way to do it. But there is an efficiency issue with that, unless you have hardware implementation of the hashing function. Yeah, like you have the TPMs or other hardware implementations. Okay, so in summary, what we did is that we described a new type of buffer overflow mechanism and how we can do that, and we outlined the approaches how to address these issues. We can have more questions. In fact, let's have a discussion.
Like, why don't we, I think we need to end the recording, so why don't we draw to a close, and then there might be some questions for you afterwards.
Okay, sure.
So, thank you.
Thank you.